So you will note that we've treated 3 problems so far. Okay, so so let me just title this boundary conditions. Okay, we have treated 3 problems so far. We've looked at mechanics. We've looked at heat transport. And now we're looking at mass transport. All right. Now, in the context of mechanics and mass transport, we've discussed the boundary conditions in some detail. We didn't quite do that in the context of heat transport, but the treatment is exactly the same. And rather than spend time now going back to heat transport, what I'm going to do is also just mention the relevant boundary conditions for heat transport. Okay. Let me think of how I'm going to organize this. Okay, I'm going to draw a big table here. Okay, and the way I'm going to do this is to use up all of this slide, and let me do this. Okay, so along the top, I'm going to put down the specific type of problem. Okay, and let me say here I'm looking at mechanics, but let's suppose we're looking at nonlinear elasticity. Okay, here I'm looking at mechanics, but fluids. And proceeding chronologically in the way we've set up, in the way we've developed our subject of continuum physics, I'm going to talk here of heat transport, which we studied in the context of thermomechanics. And finally, I'm going to talk here of mass transport, which we are now looking at. Okay. Now, definitely in the case of nonlinear elasticity, fluid mechanics, and mass transport, where we've spent some time talking about boundary conditions, you will recall, and you could do this by just going back and looking at those lectures, you will recall that we had in every case a boundary condition on what was the primary field in that problem. Okay? So let me even write out those primary field, actually let me write out the PDE for every problem. Okay, so for nonlinear elasticity, I will write it out in the context of the current configuration. So it was rho, let me see, it was second derivative with respect to time of oh, let me not do it this way. Let me do it this way. We had here the first derivative with respect to time of the velocity, but then we're doing this remembering that little x is equal to phi of capital X and time, right? So this really is a material time derivative of the velocity is equal to the divergence of sigma plus a body force. Okay. In the context of fluid mechanics also the problem is the same. Okay, I'm writing out the momentum equations in these two cases. There is also the other equation, which is the mass balance equation, right? In these two cases, right? And the mass balance equation in the context of solid mechanics or fluid mechanics is the following. It is that the material time derivative of rho plus rho divergence V equals 0, okay? And the same thing here. Okay, and then in the context of heat transport, we had the following equation. In its final form, we had an equation which took on the following appearance. It was right. It took on the form rho 0 C, where in that case C was our specific heat. Okay, we had here the material time derivative of the temperature. Okay, okay. This was equal to, I'm going to have to go down to the next line. It was equal to rho 0 R bar, where R bar was the local heating, minus J divergence of the heat flux. Okay, and in this case we had one additional term, okay, which was related to the second time derivative of sorry, not the second time derivative, the second derivative of our free energy function, which I believe in that case we were writing as chi. Okay, with respect to E and theta contracted with E dot. All right. And now finally in this case we have a simpler equation, which is just the following for our equation of mass transport. Okay, so these are the equations. I'm just going to put down the boundary conditions here. Okay, so in every case this is the equation. Now I'm going to start out by writing the boundary condition on the primary variable. Okay, in the case of nonlinear elasticity, though we've written the velocity as our primary variable, we know that we also say that the velocity is the partial time derivative of the displacement u, which is parameterized as a function of reference configuration and time, so that partial time derivative is the same as the material time derivative. Right? Okay, so for nonlinear elasticity, if you remember, we specified a boundary condition on u. We said u equals u bar on partial of omega sub t sub u. Okay, and then we also had a boundary condition on the stress, and that was sigma n, sigma being the Cauchy stress, is equal to the traction, and I think we just refer to the traction as t. Okay, and we understand that this is not time, it's the traction. Okay, all right. Now In the context of fluid mechanics, because we did not relate the velocity to the displacement, and we talked about why that is not natural in the Eulerian setting, we have a boundary condition on V itself. Okay, so we have a condition V equals maybe V bar on the velocity boundary. And we saw how this works out in the context of our boundary value problem that we solved for fluids. Now, again, in the context of fluids, we could either look at the we could look at the total stress boundary condition. Okay, so we have sigma n also equals some traction on the traction boundary condition, on the traction boundary. And you will remember that in the context of the problem that we solved, the boundary value problem that we solved for fluids, because we were doing this decomposition of the stress into a viscous stress and a purely pressure component, we could reduce this last boundary condition into a condition on the pressure. Okay, but in general, this is the form. Okay, now I'm going to write down what we have for mass transport here. Okay, and then I'll come back to heat transport and just fill it in. For mass transport, we have C equals C bar on partial omega sub C, and we have minus J dot N equals J bar on the flux boundary. Okay. Now we didn't talk about it explicitly in the case of heat transport, but likewise here we have a condition on theta, which is that theta equals theta bar on a part of the boundary where we are controlling the temperature. Okay, and that the heat flux minus Q dot N equals I think we called it Q naught, okay, on partial omega, we did this as partial omega T sub theta. So here too we would do partial omega T sub Q. Okay, in that context, when we were doing thermomechanics, we were indeed treating the different configurations due to deformations. Okay, so what we will observe is that in every case, if you look at this, at the four cases I have here for the boundary conditions, we have a boundary condition first on the primary variable. Okay, now in the case of the displacement problem, we call this the displacement boundary condition. We call this the velocity boundary condition. We would call this the temperature boundary condition, and we are calling this one the concentration boundary condition. So I want to demonstrate first of all that there is a sort of unity here, right? We always have a condition on the primary variable. Okay? Now, these kinds of conditions on the primary variable are universally called Dirichlet boundary conditions, after a French, I believe, mathematician. Okay, afraid I haven't left myself quite enough room, so I'm just going to write DBC here, okay, for Dirichlet boundary condition. Same deal, same thing here. Here I have enough, little more room. Okay, those are the Dirichlet boundary conditions. And then we have a condition on a variable that is sort of obtained through a constitutive relation involving the primary variable. Okay, so we have a condition in the case of mechanics, whether it's solid, whether it's nonlinear elasticity or fluid mechanics. We have a condition on the stress, and we've seen that the stress is obtained in both cases as a condition, constitutive relation by first taking the displacement for nonlinear elasticity, computing its gradient, going to the deformation gradient, going to other strains, and then relating the stress to those strains through a nonlinear strain energy function. Okay? Same thing with fluid mechanics, right? We relate the stress either to the spatial velocity gradient if we have a viscous component of the stress, or if we have a component of the stress, we also have the pressure component, and we've seen variously how that can be related to the volume change and so on. Okay? In the context of heat conduction, you will remember we related the heat flux to the temperature gradient. Same idea, right? We take the primary variable, compute something involving the primary variable, its gradient also in this case, and relate the heat flux to it. Okay, that was the Fourier law of heat conduction. We're going to do something like that for the flux condition as well. We haven't yet put down a constitutive relation for our flux, but we're about to talk more about it. Okay? These kinds of conditions, which are boundary conditions which are applied on variables which are typically obtained through a constitutive relation, right, are universally called Neumann boundary conditions for a different mathematician. Okay, so I have enough room here. And finally here too. Okay. Now, when we studied in the last segment or the segment before that, when we looked at variational methods for nonlinear elasticity, in that variational setting, we also made the point that that what we are here calling Dirichlet boundary conditions on the displacement field, or we previously called displacement boundary conditions, we also referred to them as essential boundary conditions. Okay, and that particular nomenclature of essential boundary conditions came from the context of the variational treatment. So people will often refer to any Dirichlet boundary condition interchangeably as essential boundary conditions. Okay? And when we did the variational principles for nonlinear elasticity, we saw why we may want to call them essential boundary conditions. Okay, but this is natural. So this is not natural. This is how it's often done. So people will often just, instead of calling something properly a Dirichlet boundary condition, they will often call them essential boundary conditions, and that may happen in these cases also. All right. Also, in the context of that problem, right, in the context of our variational treatment of nonlinear elasticity, we observed how our boundary condition on the stresses that we've identified here as being called Neumann boundary conditions, we saw how they naturally arise from the variational treatment. So they are often also called natural boundary conditions. Okay, and often this nomenclature will be extended to all other Neumann boundary conditions. Okay. Okay. Mostly just terminology, but there is some basis behind it. And the nice thing is you've seen now, or we've seen now, how there is a certain unity of the way boundary conditions are specified. We always have something in the primary field, okay? And typically, we also have something then on another field, which is obtained from the primary field, typically through a constitutive relation. Okay, and then we've seen these names, typically Dirichlet or essential boundary conditions for conditions on the primary field, Neumann or natural boundary conditions for conditions on the derived field. Okay, we'll stop here for this segment.